Every now and then, the universe does something that's completely unexpected. And we got news this week that a white dwarf star had been discovered where one hemisphere of it is covered in hydrogen and the other hemisphere is covered in helium. What? I've never seen anything like this. And so I wanted to reach out to one of the researchers who helped discover and categorize this object. So my guest today is Dr. Jeremy Heyl, who comes from the University of British Columbia, which is a university that I attended once. And we talk about how they discovered this bizarre object and what might have been the cause. So enjoy this interview with Dr. Jeremy Heyl. So, Jeremy, I've been doing this job for a long time, and I straight up had to do a double take on this story. I was like, wait, what?
Yeah.
How? What? How? What? Also, what? Explain to me what you found.
Well, what we found was a white dwarf. And we could tell it was a white dwarf for a whole bunch of different reasons. And it varies in time every 15 minutes. It gets brighter and fainter on a 15-minute cycle. So we followed this guy up to get spectroscopy. And we timed it so we could get several slices over that 15-minute cycle. And it turns out, there's a time every 15 minutes where the white dwarf, you only see hydrogen lines on it, which is not unusual for a white dwarf. That's kind of most white dwarfs.
To see hydrogen lines? Yep.
Yeah. But then no helium. Then 7.5 minutes later, you look at the white dwarf again, you see no hydrogen and only helium. And
that's not normal.
No, it isn't. So it changes every 15 minutes. It goes through this cycle. And yes, when you're halfway between the hydrogen time and the helium time, you see both, right? So it's sort of like you're looking at something where one side is hydrogen and then it rotates, and now we see the helium side and it keeps going and it reveals its hydrogen side again every 15 minutes like clockwork.
Okay, I mean, this is such an unexpected result. When you first saw this white dwarf changing in brightness, what did that make you think? Because that feels like some kind of a variable star, some kind of weird activity first.
Well, that's sort of where this project starts. We have a bunch of projects to study white dwarfs. And this particular one is led by a postdoc at Caltech, Ilaria Chiazzo. And what she had been focusing on were white dwarfs that apparently are varying in time in their brightness, with an experiment at the Palomar Observatory where they take a picture of a large portion of the sky every few nights. So then you can monitor and look for objects that vary with time and then try to find the periodicity underlining that. So she had focused, she and other people there were focused on looking at the white dwarfs, and you can divide them in two different categories they talk about. One are the binaries, and how they look in a binary is basically the light comes along and then it dips and then it comes back up again when one binary goes behind the other, one star behind the other. And the other one are called the rotators, where it goes kind of up and down, more like a sine wave rather than a big dip where they eclipse each other. So this was one of the rotators, and she's been going through all of these objects that we think are rotating white dwarfs and getting spectroscopy and seeing. We think they're all going to be weird in different ways because white dwarfs usually don't rotate every 15 minutes or even every 20 minutes. It's much longer rotation periods. So we already have a feeling that they're going to be weird in one way or another. And this one is, well, among the weirdest. There are other weird ones that are in the catalog for sure, We're just trying to figure them out one by one.
Now, all white dwarfs aren't created equally. It all sort of depends on the mass of the star and the stage of its life cycle that it's in to see what you get. So I guess what defines the chemistry that is present in the outer atmosphere of the white dwarf?
Yeah. So we'll talk the general picture. This white dwarf probably formed in a sort of special way where we had two white dwarfs that merged together to make this object. But in general, what happens is towards the end of the star's life.
Right.
What? Spoiler alert.
Oh, you just
towards the end of the star's life.
I'm trying to tell a story here. That's okay. All right. No.
I know, but towards the end of the star's life, in its central region, it's turning hydrogen into helium in a rather thin layer, then helium to carbon and oxygen, and even things like neon that are a little bit further along. And that layer where the nuclear burning is, it has a lot of nuclear burning, but it's quite thin. And as the star is aging, that nuclear burning kind of gets quite unstable, and it blows the material off of the surface of the star. And the question is, depending on exactly how that proceeds, you can end up with a little bit of hydrogen left on the surface, and underneath a little bit of helium, and then the rest of the white dwarf. Or you could end up with no hydrogen or helium at all. You could end up with just hydrogen and no helium. So you can end up with, depending on the details, different surface compositions. Now, if the hydrogen layer is very, very thin, when the star is really hot, there can be helium mixed up into that hydrogen, so you'll see helium lines. And then gradually, as the star cools down a bit, maybe around 40,000 degrees, now you start seeing just hydrogen lines, right? And then what's strange is that that hydrogen layer is really quite thin. When the star gets below around 30,000 degrees, the helium can start to mix back up into the top, and you get it to go from hydrogen back to a helium white dwarf. So when the hydrogen layer is thin, which is, it depends on the details of what happened before, you can get this transition where they're helium when they're very young, then they turn to hydrogen, and then they turn back to helium again. So this white dwarf happens to be at the right temperature where it would be going from hydrogen back to helium again, except something has messed that up in that, well, half of the star has the hydrogen still, and the other half of the star, we think, is already mixing the helium up to the surface. So when we look at it, we see, oh, it's a hydrogen, now it's a helium. Oh, now it's a hydrogen, now it's a helium. So that's what we think is going on with this guy.
Is that transition from hydrogen to helium sort of the last stage of any
in what the white dwarf does
from the star? Like,
I mean, the white dwarf just keeps cooling, right? So
right, but as it keeps cooling, will anything else interesting happen? Like, I know at the very end, it will turn into like the universe's largest diamond as the carbon finally crystallizes. But are there any other interesting behavior that the white dwarf will do?
These massive white dwarfs crystallize when they're reasonably young, in fact, right? So this particular white dwarf will crystallize not so far, from our points of view, but when it's about 1 billion years old, it'll crystallize or so, not at the age of the universe. But so what happens is if it's helium on the surface, that surface layer eventually gets so cold that it can no longer excite the helium atoms anymore. So then the spectrum just looks like has no spectral lines, so you can't tell whether it's hydrogen or helium or whatnot. It's called a DQ. We don't know, right? It's just smooth. On the other hand, if it's hydrogen on top, some interesting things can happen. First of all, hydrogen can get excited at much lower temperatures. So you can see the lines when the white dwarf is really quite old. And then there's something strange that happens, like you would imagine as things get cooler and cooler, their colors get redder and redder and redder, and that's kind of a standard idea. But with these guys, when if it's hydrogen in the surface, because they start to form hydrogen molecules in the white dwarf, that can change the spectrum and actually make them look bluer again for a little while in the bands that we study in the visual. So there is this extra, in helium, it's sort of a dead end. With hydrogen, you can start forming molecules up there in the atmosphere, and that changes their colors yet again when they're quite old, meaning 10 billion years old or so. And of course, like you said, they freeze eventually too. When they're about 4 billion years old is when the typical white dwarf freezes.
Right. And so your paper went into this observation, provided really sound evidence that this is what you're seeing, as you said, that the spectroscopy data shows helium, then hydrogen, and the timing is right, and the half and half. Like that just sounds like a open and shut case. But why?
Why?
So what is happening here?
Right. So if you look at the sun, I mean, we're familiar with the sun a lot, and you know that the sun, it has sunspots on it, right? And the reason why there's sunspots there is because the magnetic field in that region of the sun is a bit stronger, and that inhibits the boiling motion, the convection of the atmosphere of the sun. So what we're imagining on the white dwarf is you don't need a very strong magnetic field to inhibit the convection. So what's happening is on one side of the star, the field is just a little bit stronger or a lot stronger, I don't know. And on the other side, the field is weak. And on the side where the field is weak, we can have convection going on, and the helium is dredged up to the surface. So we see a helium surface. The hydrogen has been diluted by the helium, so we don't see the hydrogen anymore. On the other side of the star, the field is a bit stronger. It keeps the material from boiling, as it were, and the hydrogen just floats on top. And then we see a hydrogen side. So that is our best explanation right now, that it has something to do with magnetic field. But the fields that are required to make this happen are much weaker than the ones that we could detect with the data that we have already. So it could be that we don't see direct evidence of the field, but we don't see, things to contradict there being this field either. And in other white dwarfs, we do see the case where the field is patchy. So some places it's a bit stronger than others, or even a lot stronger than others, where we could imagine that this threshold has been met on this white dwarf, that the field is strong enough to keep the convection from occurring.
Is the magnetic field coming from a dynamo in the way that it is with the sun or the
Not
Earth
so much,
or Jupiter?
because the white dwarf, there isn't much moving inside of it. The only convection or the only motion is this convective layer right near the surface. And what I mean by right near the surface, the white dwarf is maybe this particular one about 3,000 kilometers in radius. So maybe the upper 20, 30, 100 kilometers might have this convection. So it's not like our sun, where a large radius of the sun is convecting. We also have differential rotation in the sun. The white dwarf's field, we think, is a fossil of either the field in the star that made it, in the core of that star, or how this particular white dwarf, we think, was formed because it's rotating fast and massive. We think it formed from the merger of two white dwarfs of lower mass. And that event is, it's cataclysmic. It's not that we haven't seen it happen. We have a feeling like if the two white dwarfs that they come together, if they exceed the Chandrasekhar mass, we get a supernova, a type 1a supernova. But this is one that, it just didn't add up. It didn't add up to be more than 1.35. So you're left with a white dwarf, but that's suffered a lot of indignities. And it's sort of a chimera of two white dwarfs that have been mashed together. And that was a very dramatic event with lots of currents and lots of sort of fluid mechanics that could generate a magnetic field that's now frozen into that white dwarf. And that's what we're
and so the other behavior that white dwarfs can do is they can generate novae, and this in this kind of situation, could that be a contribution to it? Because it's siphoning material from some nearby partner. It's having a thermonuclear detonation on its surface, but would that just give off a different signature?
See, for this particular white dwarf, it doesn't have a partner, so we don't see the partner there. The white dwarf itself, it's only 3,000 kilometers in radius. So if there was some other object there, like a star, it would be so much brighter than the white dwarf. We wouldn't miss it. It's very hard to hide a partner next to these guys because they're inherently so faint. They're so small, right? So this particular one we don't think has a partner. There's other objects out there that do, but not this guy.
And is there anything else like this? I mean, I'm sure when you find one, the next question you're asking is, how do we find more of these?
So the thing is, this particular object is quite far away, right? And that made it dim from our point of view and difficult to find. And it's literally looking for a needle in a haystack, because when you look out to that vast distance, there are hundreds of thousands of white dwarfs, and why is this one interesting? So that finding it is hard. But if we think about nearby objects that are similar to it, we do see white dwarfs where we see both hydrogen and helium lines at the same time, but that aren't changing. They aren't going back and forth every 15 minutes or anything like that. We see both hydrogen and helium, which tells us that hydrogen layer is really thin, or so you can see through it and see helium underneath, or in principle, that whatever mixing is going on isn't mixing that much helium up top to dilute the hydrogen entirely away. So we do see those. They're quite rare. Not a 1 in a million, but they're quite rare. And then there's one or two other objects where we see hydrogen and helium lines whose relative strengths are changing with time, but not with regularity, not every 15 minutes, and not in such a way that one element entirely disappears, and then 7 minutes later, the other element entirely disappears, and they do this swap. So this is unique in those different ways. It's regularity and the complete elimination of one element in favor of the other, and then back again. So that makes it unique. It's just, I think part of it is we're lucky that, if you imagine geometrically how this would work. So, I like to think of a model where the white dwarf is like the Earth, right? So if you think about the Earth, and the Earth coincidentally is a bit like this white dwarf, that one hemisphere of the Earth is mainly land, and the other hemisphere is mainly water. And they're oriented in such a way, if you were standing above the equator, you would see land and water every time, more or less. The water doesn't entirely go away and the land doesn't entirely go away. But for you to see that, you have to be sitting right above the equator, and the two hemispheres also have to be set up to be kind of on relative to the rotation axis, to be on the two hemispheres like that. Otherwise, you wouldn't see one replacing the other. So for this to work with this white dwarf, it's essentially we have to be very close to the equator of the white dwarf, and that we have these two sides that are the rotation. So, that those things are us being near the equator is definitely lucky. And the other part, maybe there's a reason for it, but I would think it's also luck that the field is stronger in the western hemisphere of the white dwarf than the eastern, for example. That's also probably lucky because it could have been stronger in the northern hemisphere than the southern. And then you wouldn't see them changing. You would just see half and half all the time if you can visualize that.
So I guess what tools did you use to study this white dwarf with?
Yeah, so initially the white dwarf was discovered with this instrument this survey called ZTF, Zwicky Transient Facility, which is on a Schmidt telescope, rather old Schmidt telescope. I think it's called the Samuel Ocean Telescope at Palomar Observatory, run by Caltech. So the advantage of the Schmidt telescope is it can have a large field of view. It's about a 4-foot telescope, so 46 inches it goes by. They're American, so there you go. And it can survey a lot of sky with every photograph. And basically it looks at all the sky it can see from that site every night. And one thing in particular that they do is they measure the brightness of the known stars in that field automatically. And that comes from a survey called Pan-STARRS, which is on a telescope on Haleakala in Hawaii. So they focus on these stars, measure how bright they are, and from that we can find the variable stars. Okay. Now, so far, while we just have this object is varying, but then one looks at the Gaia catalog, so now we know how far away the star is from its parallax, and we can infer that it's not only varying every 15 minutes, but it's also very likely to be a massive white dwarf. So that's the sort of finding the needles in the haystack, those first two steps. Then that star was followed up at the Gran Telescopio de las Canarias, which is the biggest telescope in the world. It's on La Palma in the Canary Islands. And there's an instrument on that called hypercam, which measures the flux from the star in a whole bunch of different band passes with very high frequency, better than a second. So then we could plot out, verify the spin period of the star, figure out how the brightness changes with time in different colors, and then follow up now that we have a really good handle of that spin period to get spectra. And the spectra here were taken at the Keck Observatory with the low resolution spectrograph, which is the workhorse. Low doesn't sound great, but it just means that you get a lot of throughput. So on a faint object, it's very effective. And that's where it was identified, we have hydrogen lines, which is usually what you get when you look at these is you find lines and you don't know what they are. Because what happens is most of these objects are very strongly magnetized. So the lines are in the wrong place and they move around as the star is rotating a little bit. And in this case, wow, hydrogen lines. It's like a normal white dwarf. And then you look at the next spectrum. Hydrogen lines and helium lines. Well, it's not a normal white dwarf, is it? And then a little bit later, the next spectrum, it's only helium lines. Wow, that's weird. So that's how the sort of discovery progressed. But it's a part of a sort of systematic campaign to look at all the objects that are massive white dwarfs and likely to be rotating quickly, meaning better than once an hour or so.
So this really sounds like the kind of discovery that will be multiplied when the Vera-Rubin telescope comes on.
Yeah. So I think with Rubin, we're going to get, a higher, it's going to be a bit deeper than Zwicky. It's also going to be better cadence. It also has on board, it's going to have U-band, so this ultraviolet filter, and that really, really helps with white dwarfs. So we can, by looking at that color in the ultraviolet versus the blue, that really helps us. We can figure out the mass of the white dwarf and all sorts of things. So it's going to be a bit more powerful. It's going to make us look a little bit deeper into the sky, but also I think even in the objects that we have looked at, just because of how ZTF, it doesn't measure it like every day, the same part of sky, whereas Rubin will catch a lot more objects with Rubin, I think, going forward.
Yeah, I mean, like whatever transient activity is happening in the sky, Rubin will find orders of magnitude more.
Yes, but Rubin's also down south, so it's looking in a part of the sky where there's a lot more of our galaxy. So that also helps a bit with the white dwarfs, but white dwarfs were really focused on close by objects. But of course, it's going to look towards the galactic center more than we can do at ZTF. So it's a whole other part of sky to discover in.
Neat. Well, Jeremy, thank you so much for taking the time to chat with me today, and congratulations to the team for making this discovery that came out of left field, and it's great, and hopefully will tell us more about the nature of white dwarfs and the universe.
Great, thanks.
A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the Galaxy Wanderers. And a special thanks to Joel Yancey, Antonio Lofi-Lara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltanan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.